Hi, hello. So this is our lecture 11, part 2, and we are going to talk about support vector regressions, okay? Same references as in the previous block. So the idea is that we are going to adapt this support vector machines to do regression problems. And basically, the main thing is that we are going to uh, look for a regression function f, okay, that we can be linear or it can be non-linear, and non-linearity will be introduced by the kernel trick as we did before. But the idea is that basically we are using a different cost function that's called the epsilon sensitive function, okay, where this function will be 0 if r is less or equal to epsilon, or be the absolute value of the argument r otherwise, okay? And we are going to use a kind of reach uh, penalty, okay? And so that's the cost function. So basically the idea is not to penalize um, small errors, and we only penalize large errors, okay? So I call these support vectors because like these um, epsilon value, the epsilon threshold here, these things work like the margin that we have in a classifier, and so this works like the two support vectors on minus epsilon and epsilon, and then you have a linear cost function. This is one the reason, and the second one is that we are going to make use of the kernel trick to introduce nonlinearity in the model. Okay, so basically, is that what I said? So the key thing also is the last bullet point in the slides, that the linear part of the loss function acts like penalizing in a similar way to the range loss, where when we have like soft margins via the slack variables. Okay, so it's basically like this. So you have here the linear line, and you have the points like the stars here. The when the error is small, case in this cone defined by plus epsilon minus epsilon, then we don't take into account this error because the errors are too small. But when points are outside the cone, then we are going to take these errors into account. So there's a parallel. See here in this slide, I'm making the parallel between the support vector regression and the support vector classifier. Okay? And if we have slack here, if we allow for some slack, that's the formulation for the linear classifier. Okay, so that's just to recall you what we saw in the first block. Okay, so it's basically the optimization problem with slack, and then we have the range loss. So this is just for you to recall what we saw in the first block. So we have the range loss plus the reach penalty. Okay, how we solve for regressions? Okay, so for regressions we have to minimize the function h. Remember what is h is the sum on the v epsilon function of yi minus f of x, okay, plus lambda square norm. Okay, and this is w transpose xi plus b, right? Okay, and so the solution, we have this general form where the w hat will be the sum, the weighted sum of the observations of the covariates multiplied by alpha star minus alpha. okay, where these alphas are all non-negative, and they solve the following quadratic programming problem here. Again, you see that we have down here the inner product. Okay? And we solved this problem under these constraints. Let me this last constraint here. Okay. So the nature of these constraints guarantees that only a subset of the solution values are non-zero. Okay? And the associated non-zero vectors are called the support vectors of the regression. Okay? And the solution is attractive because when D, the dimension of X, is much larger than N, okay, only the relevant subset of the X's are used to forecast the Y's. Okay? So we exchanging having to estimate D coefficients like in the traditional ridge for choosing and estimating only a subset of n very large dimension vectors Xi's. Okay? So it has somehow a flavor of elastic net, but instead of eliminating covariates, it eliminates whole vectors from the set. Okay? So as in the classifier case, we just need to work with the inner product of xi, xj, okay? And we can, of course, define the kernel trick by defining the kernel as the inner product of eigenfunction phi x. Okay? And we can take like the polynomials or exponentials. Okay? And the computation of this kernel only depends on the original inner product. And basically, we can substitute that the solution, instead of having a linear form, we have here on equation 5 on your slide, we have the alphas, the differences on the alphas times the kernel function. So basically, we are working with a nonlinear transformation of the data. And okay, so we have like two hyperparameters to choose, the epsilon and the lambda. Okay, and the function the epsilon, of course, is sensitive to the scale of y. So usually we do normalize the y's to have unit variance. Okay, and the two parameters have like different roles. Okay, the epsilon determines which points are negligible in determining the solution, so we don't care about these points yx. Okay, and the lambda will be a regularization. So in fact, the larger the epsilon, the smaller is the number of support vectors. Okay, and lambda is the traditional regularization parameter that we can estimate via cross validation. Okay? So it's very simple. So that's the idea. So during our live section on Friday, what I'm going to do, I'm going to go through, revise these concepts of the support vector regression, and we are going to look at an application, okay, of the News implied VIX. It's an example that I have already mentioned in several lectures. So we are going to revisit the News implied VIX and see how support vector regression can be used. Okay, so thank you very much. See you on